able to skip a step that I'm about to do here, but I have beta IB, so let's go with the beta IB. What you can say here, AVO right now, because it's not connected to a load or a source or anything, it's just going to be V2 over V1. So, oh actually yeah, V1 is across here, so we can just say that IB, so V2 equals negative, because it has to come through this way, so it's going to equal negative beta IB times RC, just Ohm's law there, negative beta IB times RC, and V1 is just V1 here, leave that as V1. IB, we can express that in terms of V1 by finding what IB is. So what's the current through here is IB. IB equals V1 over R pi. Okay. So I can just plug that in here and then the V1s are going to cancel. So that's what I'm looking for, is for those V1s to cancel. So I got beta V1, so negative beta V1 RC over R pi V1. So the V1s cancel out there and you're just left with equals negative beta RC over R pi, which you can actually just plug in those numbers because we know beta, we know RC, and we know R pi, equals negative 210 volts per volt. I just didn't want to start it before. I think that's it, right? Is that it for this one? Calculate the overall voltage gain. So then we talk about it being loaded. How does it work when you put on the source and the load? So one thing to remember is that the small signal model there for the base collector diode is identical to the small signal model of a diode. It's just determined, it looks like a resistor that's VT over IB or VT over ID. They're identical, it just looks like a diode. Okay, so then part D would be something like, or it is in this case here, calculate the overall voltage gain GB, which is from the signal voltage input. Oh, I erased the original circuit. It's from that signal voltage input all the way to the output. And so we calculated this in class. Step 1, you find AB, which is the loaded. So this one here is the loaded voltage gain. And we can actually kind of take a shortcut. I wonder if we can do this. I'm trying to think if it's fair to take a shortcut. Yeah, okay. We're going to take a shortcut because I want to talk about MOSFETs. And I think it'll be okay. I think it'll be obvious here because what we had before was we had something like a signal voltage. It was V in through a resistor here, R in, going into, oh I'm sorry, so this is our RI we called it, going into R in, which we calculated as those three in parallel. RVB in parallel with R pi. So the voltage to get from here to V1 is just a voltage divider, right? So then I'm going to skip to the output side of the circuit here. We had the output resistance. At the output side, we had the output resistance, which we found was just equal to RC, because that's all we had there was RC. And that's going to be connected in parallel with the load. I'm sorry. That looks like this. Your R out looks like it's going in that circuit. This here was the V2, and this here is the V out. Your loaded output voltage. I'm taking a shortcut just for time's sake. You can express your total using voltage dividers to get from here to here, and then a voltage divider to get from here to here. So what it's going to look like is GV equals Rn over Ri plus Rn time. Then the voltage gain of what was sitting inside that box, which we already calculated was AV naught unloaded voltage. And then times that voltage divider to get from the output over to here, times RL over R out plus RL equals, you plug in all the numbers, and anyways, it ends up being, it should be less, it should always be less. This should be your biggest one, AV should be your next biggest, and then GV should be your smallest, because we're adding load in every case. Negative 122 volts per volt. So once you have that open circuit voltage gain, you're able to add the input resistance of your source, of your generator. So if this was a signal generator, it has some resistance associated with it, which is 50 ohms. In case that would be the cable that goes in, is 50 ohms. And then at the output side, we're attaching a resistive load over here. And so again, we have a voltage divider between what we calculated in the box here. So we calculated what was in here. Maybe not. So we just did a voltage divider on either side. That's kind of all I want to say about BJTs. We did examples in class for DC bias. You should be pretty comfortable with that now. Just put 0.7 volts on there for that VBE junction, and then you can figure out the bias point from there. To find the, you always end up finding the Thevenin equivalent like we just did up there, which is always going to be those two resistors in parallel and the voltage divider to get to that point there. Flip it over to small signal, you got to find your R pi. That signal is sufficient. You can also find GM if they explicitly ask for it. So just remember these two equations. So remember, and that should be okay. That should be good. We've done a couple of these examples. This is the third example that we do. Okay. Now, I wasn't going to talk about anything new, but I think just about everybody's here. So we're going to talk MOSFETs for a minute, but we're also going to talk about MOSFETs tomorrow, which is a good thing because it's pretty close to the exam, so I want to make sure this stuff is fresh. All right. So we got so far as drawing the curves that look almost identical to BJT.